the 21st lecture on ECD. In this lecture, we will study Class B power amplifiers. Before this, we have been studying Class A power amplifiers, and we studied that a Class A amplifier works in the active region, and both half cycles, the positive and the negative half cycles of the input wave, are amplified like they are amplified for a small signal amplifier. But in a Class B amplifier, the basic difference between Class A and a Class B amplifier is that for a Class B amplifier, this amplification occurs only in during one half cycle, either positive or negative, and it remains in cutoff region. The amplifier remains in cutoff region for the other half cycle. So here is the key point. It works only in one half cycle, contrary to the Class A amplifier. Right. The example. Here is one example, or one simple example of a Class B amplifier, where we are operating this BJT amplifier in a common collector configuration. We are taking the output from the emitter terminal. The input is applied at base, and there is no biasing. The base is biased by the AC input signal. Right. So the AC input signal during positive half cycle, the AC input signal starts increasing from 0, but this junction, the base emitter junction, remains reverse biased unless this input voltage exceeds VBE, typically 0.7 volts. So as the input goes beyond 0.7 volts, greater than 0.7 volts, this junction is forward biased, and we get an output at the emitter terminal. So here it is, and for this small region, for this small portion, the output isn't there because the base emitter junction is not yet forward biased. So a similar approach, a similar region, we obtain a similar region here too, because the input voltage, when it comes back and it becomes smaller than 0.7 volts or VBE, the output vanishes and we get a 0 at the output. So here it is, so 0. So we get a signal that has some crossover distortion. This distortion is called crossover distortion. We'll study at the end of this lecture some details about the crossover distortion. But in the negative half cycle, it doesn't conduct. This is very important. During negative half cycle, the amplifier doesn't conduct because the base voltage is smaller than the emitter voltage. It's lesser than ground, lesser than 0. So it doesn't operate at all, and the transistor remains in cutoff region during the negative half cycle. So we don't have anything here. It's 0. It's 0. During negative half cycle is 0. Then during positive half cycle, we have this signal that starts after the input voltage exceeds 0.7 or VBE, and then during negative half cycle, it is again 0. So it works only during the positive half cycle, and during the negative half cycle, the output is 0. So it's very simple. If you know some basics of BJTs, you can straight away draw this output diagram, the output waveform. Right. Then how to reproduce the entire waveform, because we get only one half of the waveform at the output. During positive half cycle, we get the output. During negative half cycle, we get nothing. So how to modify this circuit, this Class B amplifier, so that we get the output during both half cycles, during positive half cycle as well as during positive half cycle as well as during negative half cycle. How would you do that? Right, that's simple. There are two techniques or two approaches to solve this problem. Which problem? The problem of getting the problem that we get only the output during only one half cycle. So how to address this problem? There are two ways. Transformer coupling is the number one solution. Solution number one. Solution number two is CST, complementary symmetry transistors. So Let's study transformer coupling first, which is very simple. We need to have two center tap transformers. One transformer at the input, which splits this input signal into two halves. And we studied in basic electronics, the first course, that if we get basic electronics course or applied physics, in the elementary courses we studied that the output of a center tap transformer is a set of outputs. It's not one output, it's a set of outputs, and they are 180 degrees out of phase with each other if they are center tapped. So actually we measure output voltage from this point to the reference, and then from reference to the point to this point, so we get an inverted signal here. Right, and we have a couple transformer, a transistor couple, a pair of transistor, where we have this NPN transistor. This transistor is also NPN. Their emitters are connected and their collectors are connected to another transformer. So during positive half cycle, this Q1 operates because we get a base voltage, a voltage here at the base that is small, that is greater than the ground voltage after it has crossed 0.7 volts threshold. And during negative half cycle, this lower transistor Q2 operates in the same way, because during negative half cycle of the input wave, we have the positive half cycle of this wave, and therefore it conducts during the negative half cycle of the original wave. Right, and then the output that we get here, we actually note output of this point with respect to the VCC. So we get an output like this, right? So we get an output because we are getting the output from the collector terminal and from the collector terminal. This means this is a common emitter amplifier, and the output should be inverted. That's right, output should be inverted. And this Q2 is also a common emitter amplifier, so its output should also be inverted. So we get this output. Both these outputs are inverted compared to the inputs, and then they are fed to a center tap transformer whose middle point is connected to VCC instead of ground. So if we note voltage here with respect to VCC, so what would we get? We will get an inverted version of this, and that is during positive half cycle it will be coming from here, from this part. So positive half cycle, during positive half cycle, this wave shape, this positive portion will be coming from here. And why is it inverted? Once again, because we are noting this voltage with respect to VCC. This voltage is smaller than VCC. So if we connect the red lead of the voltmeter here and the black lead here, we'll get an inverted voltage. This is like if we measure a 3 volts point with respect to ground, such that we get the positive lead of the voltmeter, the red lead with ground, and the black lead with 3 volts. So we get a negative here because we have connected the leads in a wrong way, right? So we haven't connected the leads correctly. We should have connected this red lead to 3 volts point and black leads to the ground. So that is why we get a negative 3 volts here. In the same way, if we connect red lead here and black lead here, we'll get a voltage that is opposite to what we see here. So the positive half cycle comes from this point, and of course the negative half cycle, it remains the same. It's not inverted. Why not inverted? It comes from here. Why is it not inverted? Because we have connected the red lead here and the black lead of the voltmeter here, and this voltage VCC is of course larger than the voltage we get here. So therefore we get the same output, the same negative half cycle here. So the positive half cycle is inverted and the negative half cycle is the same as we have at the primary side of this transformer. So this is how we get the output of for a class B amplifier. In fact, it's a class AB amplifier. Why is it class AB? Oh, I forgot to write it here. It's a class AB. They both are from class AB amplifiers. They are from class AB. Why class AB? Because for a class B amplifier, we get output only during one half cycle. So if you want to get the output during both half cycles, that amplifier is class AB. So they both are class AB, transformer coupling as well as complementary symmetric transistors. So we get the output during both half cycles out of this class AB amplifier. Right, and the class AB amplifier, the other type of the class AB amplifiers is the CSP, complementary symmetry transistor pair. This pair is connected like this, that we have two transistors Q1 and Q2, and we supply the input voltage here. So during the positive half cycle, Q1 conducts because this is an NPN transistor, and in order to conduct this, we need this voltage, the base voltage 0.7 should be at least 0.7 higher than this voltage. So base voltage should be at least 0.7 higher than, at least this base voltage should be at least 0.7 higher than the voltage of emitter. So that is why Q1 conducts during positive half cycle, but after the input has crossed VBE point and after the input is above this VBE point. In fact, this should be, it conducts, Q1 conducts only in this portion when it is positive half cycle as well as the input is above VBE. Right, and we get an output like this during positive half cycle at the emitter of Q1. So what we get at the emitter of Q2, note it is not an NPN transistor, it's a PNP transistor this time. And during the negative half cycle, we are getting input voltages that are smaller than 0. So for a PNP transistor to conduct this Q2, the PNP transistor, the emitter should be 0.7 higher than the base. So in order to do that, it should go below 0.7 volts. So to Q2 to conduct, to get Q2 to get this Q2 conducting, we must have this voltage smaller than 0.7 volts. So during negative half cycle, this Q2 conducts and we get an output like this, but we have these distorted points here. Once again, these distorted points, because it conducts only when the input goes below 0.7 volts. So to finish this lecture, let's see what the output, either it is a transformer coupled or complementary symmetry pair, the output has crossover distortion points or crossover distortion regions. This region during positive half cycle and this region. So these two regions during positive half cycle and these two regions during negative half cycle. So that is a problem. Now we actually solved at a point where we experimented with a basic class B amplifier, and we encountered a problem because it didn't conduct during negative half cycle, and then we solved that problem and we reach to a point where we get the output during positive as well as during negative half cycle. But now we are facing another problem, that is this crossover distortion. So now we are in another problem, crossover distortion. So how to solve this crossover distortion problem? There are ways to solve this, and we will discuss those in our next lecture. The next lecture will be ECD22. Right, that's all for this lecture. Thank you.